Now we need to draw a similar set of diagrams for the closed pipes. So here I have a closed pipe of length L. You could imagine this is a Coke bottle if you wanted to. The Coke bottle has a bottom on it. Or you could take a straw and put your thumb over the bottom of the straw and blow across the top of it. That's an example of a closed pipe. It has a length L. My condition for resonance is that I need a node at the closed end and an antinode at the open end. What kind of standing wave patterns can I put inside of this closed pipe? Well, over here to the right I've sketched a standing wave pattern, say for a string. If I need a node at one end and an antinode at the other end, then I could see that I have a quarter wave that would fit inside this particular pipe that would produce that sort of situation. And then if I were to look and see that I could put 3/4 of a wave in, that would be the next mode that would fit in. So let's sketch these inside this pipe. The first mode that satisfies the condition for resonance has 1/4 of a wavelength inside the pipe. Now for the next mode, I have the same length of pipe L, and I put the next standing wave pattern inside. I see that I've got half a wave here, and I've got a quarter of a wave here. And then I see that I add all that up together, and I get 3/4 of the next mode is in there. Now it turns out that that frequency is going to have some interesting multiple. This is called the third harmonic. It turns out that the even harmonics are missing in closed pipes. So this is technically referred to as the third harmonic. We'll do one more. Let's put the next harmonic inside. And I see that I have 1 1/4 wavelengths inside of this pipe. So for closed pipes, the even harmonics are missing, and these are the standing wave patterns. Numerically, let's solve a problem. This says that the speed of sound in the church is 342 meters per second. An organ pipe is 26 centimeters long. That would be roughly equivalent to a 10-inch pipe. Determine the fundamental frequency of the organ pipe if it is closed and if it is open. All right, so this would be a very short pipe that we're talking about. Let's deal with the closed one first. So I have my pipe. It's 0.26 meters long. And now I want to put the fundamental mode into this for a closed pipe. Remember, I have to have a node at one end and antinode at the other end. And I can put 1/4 of a wavelength in there, so that lambda 1/4 is equal to 0.26 meters. Now they tell me what the speed in the church is. The speed is 342 meters per second, but the speed is equal to the wavelength times the frequency. And we're asked to figure out what the frequency is. So solve that equation for F1 and make your substitutions. I get that the closed pipe frequency is 329 Hertz. Now let's do it for an open pipe. I still have a 26 centimeter long pipe, but now if it's both open at both ends, then I'm going to have antinodes at both ends. So let's sketch the standing wave pattern for that. I can get half of a wavelength in for resonance inside an open pipe, so that L is equal to lambda 1/2 for the open pipe. Now I still have a speed of 342 meters per second. And the speed is equal to the wavelength times the frequency, but now we're doing it for an open pipe, so I've got to put it in what the wavelength is for the open pipe. Solve that for the frequency. I get that the fundamental frequency if the pipe is open is 658 Hertz. So we have dealt with resonance on strings, we've dealt with resonance in open pipes, and we've dealt with resonance in closed pipes. If you've ever played in a musical ensemble, or if you've ever played a stringed instrument such as a guitar that has more than one string that's vibrating at once, then you know it's important for you to be in tune or you're not going to sound very good. When you go to tune your instrument, what you are listening for is beats, and these beats indicate that your instrument is not in tune. You're trying to eliminate beats from happening. Beats are what occurs when you have two frequencies that are fairly close to each other that are sounded at the same time, but they produce some wobbly sound as a result of being slightly different frequencies. Here are some videos illustrating beats. In this video, we have a pair of tuning forks that are slightly out of tune, and they're going to be played together. You hear that wah 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 sound? That wah 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 sound that you heard is called beats. Let's write down the definition of beats. Beats are defined to be periodic variations in amplitude, which in sound corresponds to the loudness or the volume of the sound, which results when two sources of slightly different frequencies are sounded together. So if I'm playing a trumpet and my friend is playing a trumpet and we sound them together and we're not in tune, then we hear this wobbly sound that results. There is a graphical way that this is displayed, usually on an oscilloscope, and your text attempts to show this on page 572, and here is an illustration of that.
So in this experiment, I'm going to demonstrate beat frequency and what it looks like and what it sounds like. So the first graph right here is showing a 500 hertz sine wave. The second graph here is currently also showing a 500 hertz sine wave, but I'm going to change that frequency. And I'm adding those two signals together to get this graph here. And this bottom graph here is the fast Fourier transform. It's showing the frequency content of that signal. So when the frequencies are both the same, they happen to be adding together. So right now I get single sine wave output that's at 500 hertz. If I increase my second frequency here to 501, you can start to hear a beat frequency of approximately 1 hertz, which is the difference between the two frequencies of the signals coming in. And you can see the resulting addition of those two signals is this sort of pulsating sine wave. And you can see the amplitude of the frequency response is also pulsating. So if you increase this to 502, now I got a beat frequency of 2 hertz. If you go much, much higher, you can start to see the actual beat frequency sort of overlaid on top of the carrier frequency, which is, I guess, 500 hertz. If I drop this way down to, say, 200 hertz, now I have a 500 hertz signal added to a 200 hertz signal, gives me this sine wave coming out. You can definitely see the two separate peaks on the frequency response representing those two sine waves.
In this animation that we saw, we had a display showing a frequency of one source. We'll call this source frequency 1. So maybe it was a tuning fork that was at 256 hertz. And we had a second source that was at some frequency F2. And what we were seeing here in this third printout was what's called the beat frequency. And it turns out that it's equal to the absolute value of the difference between one frequency and the other frequency. So what I end up having here is a superposition of those two things. It's an interference phenomenon. The loud part of the wah 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 sound is where constructive interference is happening. So that's this part right here, constructive interference. And the soft part of the wah wah sound is the place where there's destructive interference going on. So that happens here, and that also happens over there. So this envelope that is here that's created is what your authors are trying to show you on page 572 of your textbook, showing you the different frequencies created in two different sources. Let's solve a problem. A tuning fork has a natural frequency of 400 hertz. When the tuning fork is struck and held near a newly plucked guitar string, 10 beats are counted in a 5-second interval. What are the possible frequencies of the guitar string? Well, first of all, we need to figure out what the beat frequency is. They tell us that I count 10 beats in 5 seconds. And so when I get these 10 beats in 5 seconds, then the beat frequency is going to be the number of beats per second, which is going to be 2 hertz. So now, if I have one of my source is the guitar and the other one the tuning fork, then I can figure out what the frequency of the guitar is. Since the beats are produced by the fork and the guitar that are sounding together, then I know that the beat frequency is going to be the absolute value of the fork frequency minus the guitar frequency. And if the fork frequency is 400 Hertz, then what that tells me is that 2 Hertz is equal to 400 Hertz absolute value minus the frequency of the guitar. Well, how can I make that happen? That will happen if the guitar has a frequency either of 402 Hertz or of 398 Hertz. And so the two possible frequencies of the guitar string are 402 or 398. In summary, this has been a long lesson. We have looked at various frequency phenomena. We've looked at what happens with resonance. We have examined standing waves, and in particular standing waves in strings and in pipes, both open and closed. And we've looked at what happens when I have two sources of vibration operating at the same time and producing beats. For now, that's it.